Hey guys, this is Mrs. Clay. This video is going to cover the second half of our notes from last time. Yesterday, what we did is we went over going from the chemical formulas or chemical names of things to chemical formulas of them. Well, if you scroll down the presentations that's on Canvas, you'll notice that we have it continued. This is where we started off for class today. And what this is going to do is tell us going from the chemical formula to the name now. So with that, let's get started. Okay, so you're going to need these three things. Pause the video for a second until you grab those, and then when you're ready, click play. Okay, so just about something that we did last time. We talked a lot about lead, and I asked initially what was the abbreviation for lead on the periodic table, and it's this weird PB thing. And so I told you guys I'd do a couple more research to figure out why this thing is called PB, and it actually comes from its Latin roots. Now, the actual Latin word for lead is plumbum. That's where the PB comes. And we can think about this when we say plumbing or plumbers because they're working with lead. And so that's how they get the name. That's why we have such a strange abbreviation. It's because it comes from the Latin word. And this is actually common with other elements such as silver and gold. You'll notice that silver is Ag and gold is Au. They just happen to be a little bit strange, and that's because they use their Latin names instead of the English ones. And with that, that's just an interesting fact for you. Now let's get to what we actually want to learn about, and that's writing the names for simple salts. So this is really simple, pun there. There's only one step involved in writing this, and let me just show you it right here. You are going to be taking the formula and write the names of the elements and leave spaces in between. And that is literally all there is to going from the formula to the name. You just write out the whole abbreviation all the way out, and that's that step. Now, keep in mind that we had a couple of rules that we learned last time. These are general regardless of we're writing formulas or names, and that's that we always write the cation first and we never change the name. We write the anion last, and we drop the ending and add "ide." And then there's one other rule, but I'm going to hold back before showing it to you just because I want to do an example first. So we're going to do an example, SRF2. So following our step, we just need to find the names of these, write them out, and leave a space in between. And remembering our general rules that we write the cation first, which one of these, take a second and think about it, which one of these is the cation? Now, let's take a step back real quick. Cations have a positive or negative charge? Cations have a positive charge. What do you have to gain or lose electrons to get a positive charge? You have to lose electrons in order to get a positive. And the things that always lose on the periodic table are metals. So what we're saying essentially is when we write the cation first, you're writing the metal first. So let's find the name for Sr. That metal is strontium. And then if we find F on the periodic table, it's going to be fluorine. So what we're going to do, keeping our general rules in mind, drop the ending of the nonmetal and add "ide. Our answer is going to be strontium fluoride. Now this sounds really nice and easy, and I would like to think that it is. However, there is one other thing we need to learn that's going to kind of throw in some complications. So let's go through it. We did not talk about one of our general rules about Roman numerals. We brought these up briefly last time, and I said just write it down, and I will get back to it later. Well, right now is later. So we're going to talk about what this Roman numeral business is. So I'm going to start off first before we add those into the names, is figuring out why do we need a Roman numeral? And it's only sometimes, notice, we don't always use these. So when does it become important? Well, it depends on what metal we're dealing with. If we're dealing with a transition or post-transition metal, we need to include Roman numerals because they can have multiple charges because they can be stable in multiple ways. And this is kind of a weird idea because right now we've brought up this idea that metals and nonmetals, they always gain and lose the same amount depending on what group they're in. But we actually haven't talked about transition metals only because we said that their Lewis dot structures and electron configurations were amiss, and so we weren't going to cover them. So let me show you something, guys. We will pull up a periodic table over here, and what I'm going to do, this is just ptable.com. If I click orbitals right here, this actually pulls up some familiar things that you guys are used to. It shows the S block. Oh, it's going to come. Shows us the S block, then the P block, D block, and F block. And we know where those are. You'll also notice that it draws right here the orbital filling diagrams. So if I were to click on or hover over potassium, you'll notice that there's arrows in the 1s and the 2s all the way over. And so we see that orbital filling diagrams are a thing. And yeah, there's just lots of cool information on this periodic table. Now, one thing I'm going to do, hopefully we can zoom in. There we go. And you'll see that in the bottom left-hand corner of all of these, it has a number. You'll notice rubidium has a 1, cesium has a 1, francium has a 1. Those are representing what charges these things are going to have when they become ions. So group number 1, obviously, they all have 1 valence electron, so they're all going to get a +1 charge. We see that there's a 1 on all of these. Now hydrogen, we'll talk about later why it could be a -1 charge. Remember, it's a rebel and it kind of does what it wants, so it's an outlier. But let's look at group number 2 over here. We have helium, beryllium, magnesium. These things have a 2 in the bottom left-hand corner, which says they have 2 valence electrons and that they're going to lose those 2 to get a +2 charge. So we have a 2 common throughout. Now, if you look across, you'll see the transition metals is where the D block is. And then the post-transition metals are part of the P block. That's where we have our staircase that goes all the way down and knocks through all of these. That is where our post-transition metals lie. They are after the transitions. So let's look back at the transition metals again. You'll notice now that these things have different amount of numbers in the bottom left-hand corner, saying that they can have multiple charges. Scandium can only have 3, titanium can only have 4. Those are fine and dandy, but you look over to chromium that can have a +3 or a +6, then manganese that can have a +2, a +4, and a +7, iron with a +2 and 3, so on and so forth. So you'll notice that some of these, although they do have only one type of charge, a lot of these can have multiple charges. And we see that also same with post-transition metals. Non-metals are kind of their own thing. I'll talk about that later. But you'll notice that transition metals, they also can have multiple charges. Thallium +1, +3. Lead +2, +4, so on and so forth. So with that, let's go and look back to our slides. The reason why we need Roman numerals is because those transition and post-transition metals can have more than one type of charge. And so when we're writing out the names and the formulas, we actually have a way of indicating which of those ions we're dealing with. Now you do need to memorize these. These are the first 7 Roman numerals. These are the only ones you'll ever need to learn for this class because we'll never talk about anything that has more than a +7 charge. So take a second, write those down, pause the video, and then when you're ready, move on. One thing I will include, you can figure this out kind of on your own, but the I's stand for 1s, and then the V's actually stand for 5. And then the ones that have I's and V's in them, depending on where the I is in relation to V, either before or after, tells you if you add or take away from that 5. So for example, this IV, this is actually saying 1 less or 1 before 5, which is 4. So this is Roman numeral 4. Then we have VI, which is saying 1 after 5, which is 6. Then you have 2 I's after the V to say 7, so on and so forth. Now, why on earth is this important? Why do we need these Roman numerals when the only difference between these atoms is one tiny little electron? Well, it's because, let me show you. I have 2 examples to show you why this is important. You'll notice I put up an equation, Fe plus 2. I'm going to add oxygen with the -2 charge to it. And when those things come together, they come into a 1-to-1 ratio and give us this FeO. FeO looks like this. It's kind of a black powder. It's found mostly in the mantle of Earth's core, and we can get it occasionally when Not exactly sure what process, but it ends up in our water oftentimes. So in streams and lakes, and that's where we can find this. The actual name for this is iron 2 oxide. Notice we put the Roman numeral 2 in there. Then let's do a different example. Iron can also have a +3 charge. When it does, you'll see that the ratio of iron and oxygen is different. It's no longer 1 to 1. You have 2 irons for every 3 oxygens. So as it turns out, this 1 electron difference changes the ratios, which also changes the properties of it. Notice how this one, the physical property is this is red colored, whereas iron 2 oxide was black. There's other things that also make this unique. You guys are most familiar with this as rust. So when you see stuff rusting and it gets that red color, it's because of this stuff. Let's give it a name. Iron 2 oxide is forming. So do the Roman numerals make a difference? Yes, because iron 2 oxide is not rust. Iron 3 oxide is rust, and they have their different properties. Okay, so with that, I just want to say that the Roman numeral, the way that we can find this out is the charge of the transition or post-transition metal. You'll see there's 2 other boxes that are going to come up here, but we see that iron with a +2 charge is iron 2 oxide. Then we'll see over here that it's called iron 3 oxide because iron has a +3 charge. Now I have a couple students asking, why don't we put the plus? So iron +2 oxide or iron +3 oxide. Well, metals, do they always lose or gain electrons? Metals always lose electrons, and when they lose electrons, they become more positive. All of these right here that we're dealing with that will have Roman numerals are metals. So we'll never have to worry about writing positive or negative, because if there is a Roman numeral, it's connected to the metal, which says it's going to be a positive charge. Okay, perfect. So I'm going to blast through these real quick and then do an example, and then we'll see when my timer runs out because I only have 15 minutes to do this. So how to find the Roman numeral. I do a process called work it backwards, and the work it backwards refers to 3 steps. Multiply, then I'm going to click this, equal, and then the last step is divide. Okay, so I will let you read through kind of the explanations of it, but I'm just going to call it multiply, equal, divide, and then I'm going to show you a problem to the right on how or what I mean by multiply, equal, divide. So we're going to do this example, ZnF2. We need to, if we want to write the name, find out what these abbreviations stand for. We'll see that Zn stands for zinc and F stands for fluorine. So we're going to find this out, that zinc and fluorine are going to come together. Zinc is a transition metal, so we have to be worried about what Roman numeral we're going to use. And so we're going to find that out right now. So step number 1, multiply. We need to find the charge of one anion, the nonmetal, and find out the total negative charge because of it. Now I'm going to say this a little bit differently, if none of that just made sense. Since we do not know the charge of the zinc, and we do know the charge of the fluorine ions, we can take the charge of fluorine to help us find out zinc. So step 1, we're just going to identify what charge fluorine is going to have. We'll see that fluorine has 7 valence electrons. It wants 1 more, so it's going to get a -1 charge. And then we look at the formula and say there are 2 fluorines, so 2 times -1 gives us a total of -2 charge in that compound. Now, step number 2, we want to equal these things out because we need an overall charge of 0. So in our compound, if we have a -2 charge, then we need to have that same amount in positive. So we're going to say, and I kind of wrote as a math equation, x minus 2 equals 0. Whatever is in that blank or that x right there, that's how much positive you need. We need a +2 charge on that end. Now step 3, how many zincs are there? Well, look, see if there's a subscript. There is not a subscript, so we are going to just say, well, there's 1 zinc, we need a +2 charge, so that zinc will have a +2 charge. So your answer, I'm not going to have it written out here, and I apologize, but it would be zinc 2 fluoride. Zinc 2 fluoride. Oh yes, and it shows the work right there. Now guys, I am out of time, so do these examples. I'll have the keys online.